Okay, today we are going to do lesson 4.4. So just follow along with your notes. So here is our opening, our cumulative practice. So the big thing here is going to be the word negation. Okay, let me make it a little bit bigger. So we're going to do the word negation. So all you have to do when we are negating something is when you see the word not, we get rid of it. So instead of the ball is not blue, the ball is blue. Now, when there's not the word not in there, several nots there, we're just going to add it. So instead of the tie is white, the tie is not white. Same thing. The shirt is not yellow. And when we go to 2, oh, yay, I'm happy because all I have to do is just scribble them out. Instead of the shirt is not red, that means the shirt is red. Yeah, I really like ones like this. Now, here, graph the polygon with the given vertices. Again, what would be the best way to graph this? Desmos. Yes, I'd probably do Desmos, take a screenshot, and upload it right here. But if I look at the first one, we have 3 vertices, and the only thing with 3 vertices is a triangle. So I could name this triangle ABC. I could name it triangle BCA. I can name it triangle CBA. Any combination of the vertices, because what you do, you pick a vertex to start with and you either go clockwise or counterclockwise. Now in the second one, I know for a fact just by looking at it because it has 4 vertices, okay, that it is a quadrilateral. And then when I graph it, it comes out to be a rectangle. Now, when you name these you have to be very, very specific with, okay? So if it went like this, E, F, G, H, I have to, again, pick a vertex to start with, and I have to go in order, either clockwise or counterclockwise. So I could name this one rectangle EFGH. I could name it FGHE, GHEF if I'm going clockwise, or I could have done EHGF. What you can't do is I can't go E to G to F to H. Can't do that, okay? It has to go in order, either clockwise or counterclockwise. All right, so let's go to the first thing we have here. This is not a new concept. It's not something new. Congruent. Okay? That word congruent there. It means they're twins. It means they are alike. It means they are the same, the exact same figure. Okay? And so far, we've been talking about slides, flips, and rotations. All of these are rigid transformations. And that means that we did not change the size or shape of the original figure. So if I've got this triangle here and I'm sliding it around, oops, I caught that in with it, the size of it is the same. So if I move it from here up top, are all the measurements going to be the same? Absolutely. Okay, so that's pretty much what it's saying here. Now, we can identify congruent figures by identifying what we did to it. And it says here, the rigid motion or composition. So basically what we're going to say is, okay, these two are congruent. How did I go from the first one to the second one? Did I slide it? Did I flip it? Or did I rotate it? So if we look here in this example, the first thing that I'm personally going to notice is, oh, here's a square and here's a square. And this could be square. They're quadrilaterals. And I'm instantly counting in this first one here that there's 9 squares in there. That's the area. And it's a 3 by 3. And I come down here to the bottom and I see I got a 3 by 3 with 9. So I would say that quadrilateral ABCD is congruent to LMNP. And actually, they're squares because I can prove that they have 4 right angles, and 4 congruent sides. Now, I also can come here to this one. This is a rectangle. Has 2 pairs of opposite sides that are congruent. Has 4 right angles, but the length and the width are different. So this one does not have one it's congruent with. Okay? Now, I'm going to go do the same thing with the triangles. I'm going to look at the triangles, and I'm probably going to go, okay, this one has a length of 3, and it has a height of 2. And I'm going to check all these others. This one has a length of, 4 and a height of 3, so they don't go together. If I check this one, there's 3 and height of 2. Yay! So these two are congruent. And then you're going to see it. We're going to end up being able to say those two are congruent as well. Now, where we're going with this is, let's go back. Give you a second to write. And now I'm going to erase it. Yes, clear that page off. How did you go from this initial square? What transformations can you do to move it to here? And to me, I'm going to slide it. Okay, I'm going to say subtract or add this much from X and subtract this much from Y to get it to there. Now, if I'm looking at these two triangles, I wanted that to be a different color. There you go. That looks like I rotated it. Okay? Looks like I rotated it. Now, I could also do a slide and then a flip. It's just a matter of, do you want to get it in that new position in one transformation or two? And then if I'm going here from these two, it looks like all I did was I flipped it across the x-axis. And that's what we're going to be doing in this section, is trying to identify what's happening. And so when we're talking about, here's another term that they're wanting to give us, a congruence transformation. This is basically saying you're doing transformations so that your original image, your pre-image, and what you end up with are the exact same figure. You didn't shrink it, stretch it, enlarge it, nothing. That what the figure you started with is the exact same figure you ended with. All right, with me? Okay, so now let's describe this congruence transformation. Now, here's where it gets kind of interesting. If you're working with a partner, you both might come up with a correct answer, but they're different. Okay? Just like if I was standing at my desk and I needed to get to the front door to go out of the classroom, there's several different routes I can take to go from my desk to the door. Does that mean one is right and one is wrong? No, it just means I have options. So if we look at this initial parallelogram here, how do I get it from being in the second quadrant to the fourth quadrant? Okay, and let's go down here in our solution. There's several ways that I can do it. And what the book is saying to do is they're going to flip it over the x-axis. And when it's flipped from here to here over the x-axis, you can see we get our new figure, D prime, C prime, B prime, A prime. And then from there, it looks like when we go from here to here, we just did a slide. So the first one we did was a flip, and then we slid it. Now, I could also do it a different way. I could have chosen to slide it here, and then from here to here, I could have flipped. I'd get the exact same thing. Okay? Now, here's the theorem I'm getting ready to introduce to you, and it's a lot. I'm just going to tell you. I'm not going to read the way that they've said it. I'm going to try to tell it to you in everyday language. Okay? So basically what you have here is you have line K and you have line M. And they are parallel. I know that because they have the arrows. Okay? And you can see I just drew them. So if we are starting here with line BA, I know that K and M are parallel. And you can see there's a distance here in between them. If I take BA and I flip it, Let me change the color. If I flip it over the first line, and then I turn around and I flip it again over the second line, okay, one, I know that these two will be parallel to each other. Okay, so first of all, I know that BA and BA double prime are parallel to each other. The other thing, and what they're wanting you to know, is that this distance here from A to A prime, I gotta turn that tool off, from A to A prime is going to be twice the length of from our two parallel lines. So if I told you, in other words, this distance right here is 5, that middle distance, oh, I don't like that color. I know y'all are like, Edward, stop. So if I told you this distance right here was 5, you'd be able to tell me that the orange distance is 2 times 5. And that's what they're wanting you to get out of it. Okay, if we take that line BA and we reflect it over K, then we reflect it over M, and K and M are parallel, the distance between BA and BA double prime will be twice the length as of the distance between lines K and line M. Okay, so now let's look at this. Okay, here I've got two parallel lines, K, M. So there's my two parallel lines. And I have reflected EF over each one of them. Okay. Now, what I would know is if I know the length from here to here, then I would be able to say that this length is twice that distance. So if I measure the distance here and it's D, from F to F double prime is going to be twice that. Okay. I also can tell you that EF is congruent to EF prime and EF double prime because they're rigid transformations. I can also tell you that EF and EF double prime are parallel. Okay, so now, instead of doing it with parallel lines, we're going to do it with angles. Okay? So again, I'm going to try to give it to you in everyday language. So here we've got K. Use my line tool. And then we have line M. And you can say K and M have created this angle right here. Color it in green so you can see it. They intersect and have this line here. Now, we're going to go and take this line segment, AB. I can't really color it well. AB, and we are going to reflect it over each one of our lines. Okay? Now, for one, AB prime and AB double prime are going to be congruent to AB because we're doing a rigid reflection. But here's what the book wants you to get out of this theorem. If I know the measurement of that green angle, then the measurement of this orange angle here will be twice that. Okay? This orange angle here will be twice the measure of the green angle. So if I told you this green angle here had a measure of 60 degrees, okay, this is the green one, then the orange one would be 2 times 60 degrees or 120. Okay? So hopefully I put that in good everyday language for you. So if we look here, here's a great example with it. We've got some hearts here. Yeah, Valentine's Day, color it in. Yay, there you go. Okay, so we're going to take this heart and we are going to reflect it twice. Now, they're coming back and they're going to ask you, what is the degree of rotation that I measured it from the first one to the third one? Well, we don't know. But what we do know is that this angle right here is 60 degrees. So if that middle angle is 60, then the angle from first heart to third heart is going to be twice that. 2 times 60, which is 120 degrees. Yay! Okay, number 1. Here they want you to identify congruent figures. This is going to be a lot like what we did earlier. Again, the first thing I'm going to probably do is go triangle, 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 and compare those. And then I've got 2 parallelograms. So first I'm going to check. I'm going to do height and width area to see are they congruent. And when I do that, and I'll kind of color them, use my highlighter, I do know my two parallelograms are congruent. Okay? I do know that these two triangles are congruent and that these two triangles are congruent. Unfortunately, this little guy is by himself. He's sad. He is not a twin with anybody. And so then if we want to talk about what is the actual transformation that we did, if we're talking about the two parallelograms look like we did a 90-degree rotation. Okay, so it looks like it's 90-degree rotation there. If we're talking about the two yellow ones, it looks like we did a flip about the x-axis. Okay, so this one's a 90-degree rotation. And if we're going from one purple to the other, it just like all we did was slide. Okay, we just slid it up there. We didn't rotate it. We didn't do anything. Okay, now let's look at 2. Describe a congruence transformation that maps ABC onto ABC prime. Okay, well notice B is here and B is here. A and C are in the same location, so we didn't do any type of a flip or a rotation, because if we did, then they would be in different areas. So this is a slide. And if we want to describe it, all I need to do is come over here and I'm going to look and say, okay, for B, I went 1, 2, 3, 4, 5. So I went 5 over. So that means I have X comma Y is going to change to X plus 5. Oops, didn't mean to do that one. And then Y, so now I'm going to check my Y. What did I do for my B on my Y? I went up 1, 2, 3, 4, 5. Y plus 5. Okay, it's a slide. Okay, so here, my given information tells me that this width right here is 4.3 inches. And they want to know what is the length from D to D and E to E. Well, that's one of our theorems that someone proved. It is going to be twice the length of the distance between the two lines. So my answer will end up being 8.6. And then 4 is very interesting. So basically what they did is they went from fourth quadrant to first quadrant to second. So they did 2 transformations. They flipped it, and then it looks like they rotated it. And so the big question is, kind of like a game, hey, I can move this to the new position in 2 transformations. Now you're coming back and go, I can move that in 1 transformation. And that's what they were wanting to know. How can you go from fourth quadrant directly to second quadrant? And you can do a rotation. And more importantly, it's a rotation of 180 degrees. Okay? 180-degree rotation. And that's 4. Woohoo! Yay! Now we're going to 4.5. Gotta love it. Ready? Okay. Now, here we're getting into something completely new. We're getting into dilations. Now, when I hear the word dilation, and I think everyday language, the only time I really think about it is when I go to the eye doctor. And when you go to the eye doctor, you have to get your eyes dilated. And we all know what that means if you've been. That means your pupils are really, really huge. So when we talk about a dilation here, okay, we're going to have a dilation that has a point that will be our center of dilation and will have a scale factor. Now, we do dilations all the time. Like I'm going to do it right now on the screen. I put my finger on my screen, which will be my center of dilation, and then I'm going to make it bigger, or can I make it smaller? These are dilations right here that we perform every day on our iPad. Okay? Now, this scale factor is going to mean, am I enlarging it or am I shrinking it? A scale factor of 2 means I'm doubling its size. A scale factor of 1/2 means I'm going to shrink it. And this is where we get here. If your K value is greater than 1, we are enlarging it. If it is between 0 and 1, then that is where we're shrinking it. We're reducing its size because we stop at 0 because when we get to 0, we've pretty much erased whatever we're looking at, okay? Now, you're going to see some problems where it's going to give you a scale factor of -4. Technically, the scale factor is 4, but the negative is going to make you move it and change it in direction. It's going to also kind of perform some type of translation with it. So let's identify. In our example here, they're wanting to know, is it a reduction or is it an enlargement? How do you find that out? Well, first I'm going to go here and I see point C, and then I see here point P and P prime. So P is where we started, and we ended at P prime. So this tells me right now I am looking at a dilation. Okay, I know instantly. I took that crayon and I made it bigger. Okay, so now I've answered that question. It's an enlargement. Shouldn't have put dilation. Should have put enlargement because dilation could be either. Sorry about that. And I can't write. So it's an enlargement. Now they're wanting the scale factor. Okay. So for the scale factor, what you want to do, you can see it right here. It says put CP prime over CP. So the length of CP prime is 6 and the length of CP is 3. That's going to give me a scale factor of, I can't do my math, 2. Now, here is the number one problem students make. They don't know which number goes on top and which number goes on bottom. And I make this mistake all the time. I might look at this, and when I go back up here, I'm going to erase it. I see the number 3 and 6, and I instantly go, okay, K is 3 over 6, which is 1/2. That is incorrect. And I know it's incorrect because I already identified this as an enlargement. And if it's an enlargement, then K must be greater than 1. And so since I came out with 1/2, I'm like, no, that's a shrink. I instantly know I should have put the 6 on top and the 3 on the bottom. So here's a good rule of thumb. When you're making it bigger, the bigger number goes on top. When you're making it smaller, the smaller number goes on top. Hope that helps you remember it. Okay? So now, coordinate rule for dilations. Okay, coordinate rule for dilations basically says, and the important words here is centered at the origin. If we are shrinking or enlarging centered at the origin, and we are told our scale factor, which is K, all you have to do is multiply each X and Y coordinate by that scale factor. It's kind of cool. Now, right now, I might have lost you, so let's do an example, okay? Now, here, we've already said that K has to be greater than 0, okay? Now, and this is what I told you earlier. When we have a scale factor that's negative, it is the same as doing a dilation followed by a rotation of 180 degrees. So we really can't have a negative scale factor. But when we do that, when we multiply our scale factor by -1, we are doing a 180-degree rotation about the center. Okay? So let's look at this one. Here's our first one. Here's our triangle. And so for the first one, we want to use a scale factor of 1/2. And so I'm going to go down here, and you can see I've listed all of them the exact same. And then you're just going to come through and you take that 1/2 and you multiply the first one, -4 times 1/2. Okay, and we get -2. Each one of these numbers, we go through here, -4 times 1/2, 2 times 1/2, -2 times 1/2, 2 times 1/2, -2. And you can see our resulting numbers are right here on the right. Now they're giving us a scale factor of -2. So again, that's a scale factor of 2. The negative makes us do a 180-degree rotation. And you can see that here. We rotated it 180 degrees and we enlarged it. And so you do the exact same thing. You take all your original points and you go through and you multiply each one of them by -2. So -4 times -2 gives me 8. 2 times -2 gives me -4, and so on. We get our 3 new coordinates. You can plot it in Desmos, take a screenshot, and upload it. And there you go. Now, for number one is asking us to find, it doesn't go with this, okay? This graph is kind of confusing. Goes with number 1 there. So it's first asking, is this a reduction or is this an enlargement? So I'm going to go and I'm going to look here. Here is C. It's telling me that the small figure is P and the large figure is P prime. So this little one here is our original pre-image, and then the outside one is our image. So we started with the small one and ended with the large one. So that tells me I have an enlargement. Okay, boom, I got that one answered. Now, the second thing it wants to know is, what is the scale factor? When it's an enlargement, remember the bigger number goes on top. So 27 on top, smaller number on the bottom, we have a scale factor of 3. So I can tell you I enlarged this rectangle 3 times its size. Okay. Now let's look at this one. This one's pretty cool. I like this one. Because all you're doing is you're taking this scale factor here of K, and we're just going to multiply everything times 4, times 4, times 4, times 4. Okay, all of them, just times 4. And so I get P prime is going to be 4, 8. Q prime is going to be 8, 8. R prime is 8. No. 4 times 4 is not 8. Haha, it's 16. And then -2 times 4 is -8. And then I'm going to get S prime is -4, -12. Again, now I can, if you needed to see the graph, plug it in Desmos. And then here we have A, B, and C. Same thing. You're just going to turn around and take your K factor and multiply it by all of those. Okay? Now, something that I'm not there to tell you, but I'm going to tell you about it here right at the end. I had a student in first block that came and showed me something amazing in Desmos. Absolutely amazing, okay? If you go in Desmos has a lot of functions in it. There's tons of functions. I've already told you about how you can write polygon, parentheses, and then like put in your points, 3, 8, and it would graph the triangle for you, okay? Well, there are some new functions that we just found that are amazing. Amazing. The first one is you can write the word distance, okay? It'll give you parentheses and say, I want to know the distance between the point 3, 1 and -8, 4. If I put it in Desmos just like this, is it going to give me the distance? Y'all, this is huge because this is basically doing your distance formula for you. This is a whole lot easier than the square root of r squared over run squared. Okay, hopefully you're all cheering and you're like, woohoo, that's awesome. Now there's a second one, and I know several of you struggled with this one. There is a midpoint function. So you type in the word midpoint, and again, I might say, what is the midpoint between 2, 1 and 8, 10? It is going to come out, and it's going to give you a point, okay? Now you're going to have the little box down here which says label. I'm going to check it because then what Desmos does is Desmos will graph the midpoint, and when you click label, it's going to come in here and give you the exact values of it. So for those of you that have been struggling with distance formula and midpoint, hopefully I just made it a whole lot easier for you. Okay, if you have any questions, feel free to hit me up on Google Classroom or Remind and get started on that practice, and see you when I get back.